Okay, I'm recording now. So again, we're working through the virtual lab on collisions. It might initially say week 3, but obviously we're in week 4. So it's kind of reviewing stuff from last week. And I did click on this link here. So it did open up for us, which is right here. If you read through this, it says simulation models the following scenario with 2 carts on a low friction track. Okay. So I guess you have these motion sensors also connected. And we're going to be exploring momentum and energy. So momentum object is this mass multiplied by its velocity. We know this. Momentum is a vector, so direction is important. We know this also because velocity is a vector. So question number 1. In this experiment, the motion is one-dimensional. How can you account for the direction of momentum in this case? Well, you can kind of consider usually what you want to do. This seems kind of like open-ended, so I'm not 100% sure what particular answer would be best, but I suppose we could say consider because usually you do want to have the positive direction well defined. So consider motion to right to be positive, I guess. So if momentum are both positive or both negative, then they're in the same direction. So you guys a little chance to copy that down. For kinetic energy, you're squaring velocity. Remember, energy is not a vector, so don't really worry about that because it's always going to come as being positive. Because again, you're squaring the velocity and mass is not negative. So hopefully that makes sense. Hopefully you're okay about that. And usually the rule of thumb is anything going to the right, consider it to be positive, anything to the left, consider it to be negative. So if you do that, then you have the velocity, the direction of the velocity defined, and the momentum follows the same thing. So at least you have a consistency. And I'm guessing that's what they're looking for that question, 100% sure. There's a lot of background stuff, right? So any questions so far? Nope. Cool. So I'm going clear. Question number 2. In this experiment, you'll be determining whether momentum and kinetic energy are conserved. What does it mean for the quantity to be conserved in a collision? It means that the total momentum in KE for collision equals the total in KE after collision, just so you know. So before and after, you expect to be the same. And one way to classify collisions is in terms of kinetic energy as follows. So elastic is what we're interested in. That's when it's conserved. Inelastic, when the kinetic energy is lost, usually to friction. Superelastic kinetic energy is larger after a collision. That's kind of weird. We won't really look at that. Complete inelastic, when objects stick together after the collision. We'll look at those situations, I suppose. But that's what we are noticing here. So now let's actually play around with the simulation. I'll play around a little bit with it and then let you guys do that in groups. So spend a few minutes playing the simulation, familiar yourself what it can do. And I guess they're saying here for cases 1 through 3, collect data, use them to collect data and complete calculations to show the system momentum, the total system kinetic energy, before and after collision. So as you imagine, I is going to be before, F is going to be after. And you're collecting velocity values, right? And once you do that, then you can calculate momentum values and the total momentum and do likewise the kinetic energy. Maybe I'll do case 1 with you guys so you can at least see that in practice. And I'll let you guys kind of draw your conclusion, do the other cases, obviously. And case 1 is elastic collisions, keeping velocity setting at 1 for this phase. With actual cards at mags and the ends set face one another with the mags ready to repel. So let's look at this right now. Let's see what's going on here. Let's just kind of play around with it just a little bit. So kind of get myself familiar here. It looks like cart 1 velocity is defined as 1 meters per second. Cart 2 is nothing. So cart 2 is obviously at rest. And you could totally play with that a little bit. For this one, you can obviously play with that too, but we'll keep it motionless. The elasticity, you could change that. You know, that's completely inelastic. That's somewhat inelastic. That's totally elastic. The masses we could change. So both the same masses, you could double the mass of one, and that one made double the mass of the stationary one, or triple the mass of the moving one, or the other end. But we'll keep them the same for now. Make it easy. And here are momentum bar graphs. We could look at a momentum versus time graph, energy versus time, velocity versus time, position versus time. But I think we'll do this instead. So we can see how the momentum, and the blue is before, the orange is after, so the transfer, and the green is after. Okay. So I think we're ready to kind of play this and see what happens. So it looks like it's coming at it. It's taking a sweet little time. Okay, so now the cart 1 velocity comes to rest. And obviously we have that. If I were to speed it up just a tad, so you can see what's happening is that the blue is a momentum of this red cart before collision, and then it's transferred in the orange, and then of course it all comes to the green, and the total system stays the same for the momentum. So that's for our momentum bar graph. So again, if I do that, and I think what we're trying to accomplish here, I don't really care for that. Let me reset. So let's actually go through one of the cases right now. So we'll do 2 different collisions, one with the same mass and one with double the mass, and we'll change initial velocities. And then we'll get their final velocities. We'll have to record that. And once we do that, then we can fill out the rest of this stuff here. Okay. So the other 2 tables. All right, so let me go back to the simulation again. So we are going to set this out to -3. And we're going to set that one to +6. Masses are the same. And we're going to pay careful attention to the change in velocity afterwards. So right now, it's 6 for cart 1, and that's going to the right, and -3 for the blue cart, that's going to the left. And their masses are the same. So let's play right now. So let me pause. So now we see that the velocity of cart 1 is -3. So you're going to put -3 right here. As a +6 meters per second. So now I can calculate the momentum of the first cart, the final momentum, which of course is going to be its mass times its final velocity. So it's going to be -3 kg times meters over seconds. And if I do for the second cart, that's going to be +6 meters per second. So the final momentum, if I add up, it becomes 3 kg times meters per second. So we do see momentum is conserved. If I calculate the energies, so remember 1/2 mv squared. So you do 1/2 times the mass times the velocity squared. So if I square 9 and multiply 1/2, I get 4.5 joules. If I do for the second card, the final, 1/2 mv squared, so 1/2 times 1 times 36, 18 joules. So it looks like that's conserved also. Get 22.5 joules. So I've done the first row for collision 1. Now you're going to do you and your partner is you're going to change the mass. So you can go back to the simulation. It should be pretty easy to work out. So go ahead and reset that. You're going to now do that. And you're going to work it out and collect the data and calculate the momentums and energies. And then you're going to do the next case. Then you do case 2, kind of work that out. But you're going to change the elasticity to 0. In case 3, you're going to change it to 0.8. And then you're going to answer some of these questions here. Is momentum conserved? Blah, blah, blah. Explain using answers. Explain how the bar graphs on at least one graph support your answers. I am going to have to do page 4 also. I decided we should. Is kinetic energy conserved? Explain blah, blah, blah. Describe the differences in net kinetic energy. After collision between these 3 cases. And then I think that's as far as we'll probably get today. So we'll get to the end of page 4. So we'll do about half of this today. So I'll give you guys about 20, 25 minutes probably to collect that and work this out and answer the questions. And I'll hop into your rooms and make sure you guys are doing okay. So let me go ahead and clear this. Stop sharing.